Okay, November 2024, paper 6, variant 3. Question 1, the student investigates the cooling of water in different sized beakers. He used the apparatus shown in 1.1. Beaker A and Beaker B have graduations as shown in figure 1.1. So Beaker A has graduations of 50 centimeters cubed, 100 centimeters cubed, and B has 100, 200, and 300. First of all, can I find the theta R? Can I find the room temperature? Yes, the room temperature is 22 degrees Celsius. Describe one technique to use so that the temperature reading is as accurate as possible. Take the reading perpendicularly. Take the reading perpendicularly to avoid, parallax error. Avoid parallax error. Okay, and then in B, he puts the thermometer, suggests one possible source of inaccuracy in the procedure, even if it is carried out carefully. So he puts the water in. What could one source of inaccuracy be? One source of inaccuracy could be that he is adding 75 centimeters cubed of water, right? And then the graduations in B or in A aren't that accurate actually. Why? Because in A it's 50, then 100, and in B it's 100, 200, 300. So to find 75, it should be somewhere in the middle. Can you find the middle? Okay, can you find the exact midpoint between 50 and 100? It would be a bit difficult, right? Can you find the 75 mark exactly on B? Again, it would be a bit difficult. So actually, this is the problem. This is the difficulty. Okay, it is quite difficult to estimate the 75. It's difficult to estimate 75 centimeters cubed, not 75 degrees, 75 centimeters cubed. Okay, so table 1.1, you have beaker A and beaker B. Write the conclusion describing the effect of changing the size of the beakers. So beaker A was smaller, beaker B was larger. Difference between the starting and ending temperatures of A is 9.5, right? 9.5 degrees Celsius. In B, it was from 80 all the way to 63.5, which is 16.5, which is quite the difference. Meaning that as you increase the volume, beaker A was larger. As you increase the size, the rate of cooling also increases. As the size increases, the rate of cooling increases. Then we need to write down the numbers. Beaker A, which is smaller, it started off at 82.5 and ended at 73, which is a difference of 9.5 degrees Celsius. In beaker B, the difference was from 80 to 63.5, a difference of 16.5 degrees Celsius. Okay. Students in other schools do the same experiment using identical apparatus. State one variable they need to control the initial temperature of the water. Okay, the initial temperature of the water. You can say the volume of the water. Okay, can I find the rate of cooling X in beaker B? Yes, in beaker B it was from 80 to 63.5 and then divide by 80. So 80 minus 63.5 divided by 180, which is a rate of cooling of 0.0917 degrees Celsius per second. Do not forget the unit. Now, the student thinks that more thermal energy is lost from the surface of the water than from the sides of beaker B. Suggest an additional experiment. Okay, so more thermal energy is lost from the surface of the water in beaker B than from the sides of beaker B. So just an additional experiment that she can do. What can she do? What could she do? She could add a lid. She could use a lid to cover beaker B. To cover beaker B. So just how the cooling rate of the water in beaker B in this additional experiment compares with the value of X in E if her idea is correct. So if her idea is correct and she adds a lid, would this affect the rate of cooling? Yes, it would affect the rate of cooling. How so? The rate of cooling would actually decrease. So the rate of cooling will decrease. Okay, it decreases much less than, okay, much less than x, which was the initial rate of cooling. Okay, now moving on to question 2. On figure 2.1, draw a voltmeter connected to measure the potential difference across the resistor. So across the resistor, we can draw a voltmeter. Soon connects the crocodile clip, measures V0, V note, voltage, which is 3.2 volts. 3.2, let me write it down again. Okay, 3.2 volts. And then she measures the current and writes it down in the table. The current is 0.18. Now we have a table and we have a graph. Plot a graph of L on the y-axis, I on the x-axis, I on the x-axis. You do not need to start the axes from the origin. Okay, so as for the length, 20, 30, 40, 50, 60. Okay, I guess we can write them down as they are, 20, 30, 40, 50, 60. Or if you want to start with 10, it's okay. 40, 50, and 60. If you want to start off with 10, it is okay. What about the current? It starts with 0.18 all the way to 0.42. We need to stretch out these numbers a little. So if I start with 0.10, 20, 30, 40, wouldn't be bad. What about 0.15, 0.15, 20, 25, 30, 35? No, it would not be enough. You need all the way up to 42. So we can start with 0.10, 0.20, 0.30, and 0.40. Okay, not too bad. First point was 0.18 and 20, 0.18 and 20, which is over here. And then 22 and 30, 22 and 30 over here, right over here. So this is 22 and 30. Next point is 30 and 40. This is easy. Again, you need to use small x's. Make sure your pencil is quite sharpened. 39 and 50. 39 and 50. This is 39 and 50. And the last point is 42 and 60. So we have 42 and 60 over here. This is 42 and 60. We need to draw a best fit line. Okay. Best fit straight line. He was very accurate. He was very... So let's draw a straight line. Straight line would be drawn somewhat like this. Actually, let me draw it again. Yeah, this looks a lot better. You have 1 point above, 1 point below, and the 3 other points are almost on the line. So this is a very accurate representation of the line. Yes, these 3 points are on the line, 1 point above and 1 point below. Can I find the gradient? Yes, I can find the gradient using the triangle method. So you have to draw a triangle using 2 very distant points, such as these 2 points. If I use these 2 points, it would be 60 minus 20 over 0.42 minus 0.18, which is a gradient of 0.42 minus 0.18. This is 166.6 or 167. 167. Yeah, this is the gradient, 167. Can I find the resistance using this equation? Okay, so G, the gradient, 167 times V naught, which was 3.2, divided by 100, times K, which is 1. 167 times 3.2 divided by 100, this is 5.3. Okay, 5.3, and do not forget the unit, which is ohms. The ohms, the unit is already written. Suggest one practical reason why other students might not obtain the same result as the student. Other students conducting this same experiment have different results. Why so? Because they have a crocodile clip, right? So this crocodile clip might not be exactly at the same distance. Or another problem might be that the thickness of the resistance wire isn't the same. The thickness of this resistance wire is non-uniform. So the distance of the crocodile wire, okay, crocodile clip isn't the same, or you can say it's a non-uniform wire, non-uniform wire, okay, clip. The resistance wire can become very hot during this type of experiment. So just one change to the apparatus that prevents this. You need to decrease the voltage and the current. You need to decrease the EMF, okay, the EMF of the source and the current. Student investigates the refraction of light by transparent block. So you have a ray trace sheet. Let's see. Draw normal to point N extending above AB. The upper point L, extend the normal downwards until it crosses CD. Okay, the point where it crosses CD is F. Okay, so we need to draw normal. Okay, normal. It has to be perpendicular. Make sure it's perpendicular. Okay, the top point would be L, and this normal should extend until it crosses CD, and this point would be F. And then student draws line EN. Can I measure the angle theta 1 between EN and the normal? Can I measure this angle theta 1? Yes, I can measure this angle theta 1. Using the protractor, this angle would be around 15 degrees. 15 degrees. Soon place two pins P1 and P2. Can I measure the distance between these two pins? Yes, I can measure the distance. Distance between these two pins is very small. It's actually 3.5. If your reading or if your measurement is slightly less than 3.5, it's okay due to the printing error. Suggest whether the two pins are at a suitable distance. Is this a suitable distance? 3.5? No, not suitable. Okay, not suitable. Why isn't it suitable? We need a larger distance. Okay, a larger distance. We usually say at least 5 centimeters. At least 5 centimeters. This is a suitable distance. Student views the image of P1, P2. Draw a straight line between or through P3 and P4. Extend this line to cross NF. The point where it crosses NF should be G, where it crosses CD should be H, and then join points H and N. Okay, so G and H. P3 and P4. We need to continue line P3 and P4 until it reaches, okay, until it reaches. So this point is G, this point is H, right? G, okay, and then H, join points H and N. Can I draw a line HN? Yes, I can draw this line. Let me write H on the other side. Let me write H over here. So this is point H. And then draw a point, a line NH or HN from N all the way to H. This is a straight line from N to H. I'll draw it again. I'll try to make it as straight as possible. Definitely, you are using the ruler. It should be 100% straight. And then, can I measure the length HN and the distance between H and G? Can I measure HN and then HG? Yes. HN is longer than H. Yes. HN is 6.1. This distance is 6.1. And the other distance is 4.2. Again, if your readings are slightly less, it would be okay. Not by a huge number, not if your distance is 6, only 6 is okay, maybe 5.9, that might be acceptable. If your distance for B is, for example, 4.1 or 4, again, it might be acceptable. Why? This is due to the printing error. Printing error. Calculate the value n for the refractive index. N equals A over B, so 6.1 divided by 4.2. What is 6.1 divided by 4.2? This is 1.5. Student repeats the above procedure for an angle theta 2, 40 degrees. Draw a line through P5 and 6 until it meets GH. The point where it meets GH is K, where it crosses CDR. So until it meets GH, till it meets this red line. Okay, let me use another color. For example, I'll use this color. So P5 and 6, P5 and 6, until it meets GH, right? Okay, until it meets GH. This point of intersection is called what? This point of intersection is called K, and then the other point is R. This point is K, and this point is R. I know my lines aren't 100% accurate, but again, when you're drawing, it should be a lot more accurate than this. So you have K and you have R, and then he needs me to measure some distances. First of all, I need to measure the angle between RK and GH. Between RK and GH, we need this angle between the red and purple lines. Can I measure this angle? Yes, this is angle alpha. He wants me to measure angle alpha. I can't do that using the protractor. This angle should be around 25 degrees. This angle should be around 25 degrees. Another student suggests that angle alpha should be equal to the difference between theta 2 and theta 1. What was theta 2? Theta 2 was 40, okay, and theta 1 was the angle we measured, which is 15. So 40 minus 15, is it equal to 25? Yes, it is. 40 minus 15 is actually equal to 25. So yes, he is correct. Yes, it is equal. Why? Because 40 minus 15 is actually equal to 25. So the values are close. Even if your values, for example, of the alpha was, for example, was 26 or 24, or theta 1 was not 15, maybe it was 16 or it was 17 instead of 16, maybe it was 14, for example. Okay, if you had these values, it's okay, then the values are still close within the limits of experimental accuracy. The values are close, okay, and within the limits of experimental accuracy. Suggest one technique to use in this type of experiment to ensure that the results are accurate. One very important technique is to use thin lines. You have to use thin lines. Plan an experiment. Okay, so he's investigating the speed of a small, okay, trolley moving down a sloping ramp. Plan an experiment which will enable her to what? To compare the effect of different angles on the speed. So basically, she is changing the angle and she is measuring the speed. The apparatuses are the long ramp and a small trolley. It's quite obvious we need a lot more apparatuses, and we need to explain, suggest a possible source of inaccuracy, state the key variables. First of all, what is my independent variable? My independent variable is the range of values. Range of values. I will be changing the angle of the slope within the limits, again, we need to talk about logical numbers. What could some logical values for the slope be? If I say 10 degrees, 20 degrees, 30 degrees, 40 and 50 degrees. Yeah, these are some logical values. Don't go above 90. Not even 90. 90 is would be wrong. 90 would be a vertical drop. This wouldn't be a slope. Okay, so maybe up to 70, for example, 75. That's way too steep for a slope. So these are the range of values. What about the controlled variables? The controlled variables. Controlled variables. You have a car moving down a slope. Controlled variables would be what? Uh, wouldn't it be the distance traveled down the slope? Yes, the distance traveled. What about the starting point on the slope, on this ramp? Yes. Okay, so let's write them down. So distance traveled. Okay, between 2 points on the slope. Between 2 points on the slope. The starting point on the ramp. On the ramp. Okay. Um, let's write down the apparatuses. Main apparatuses for this question would be, for example, the stopwatch, right? You need a ruler, and you also need, hmm, and you also need a protractor. Okay, protractor. Somehow I messed up writing down a protractor. It's okay. It's okay. What about the? Let's check out. What did we do? We listed the additional apparatuses. We need to write down the steps. A possible source of inaccuracy. Okay. What could one possible source of inaccuracy be? Well, this is actually quite a short slope, isn't it? It's a short ramp. It's a toy. So starting and stopping the stopwatch would be a source of inaccuracy. It would be quite difficult to measure the time accurately. How can I overcome that difficulty? By repeating and taking average, right? Now, the steps: release, okay, the trolley from a fixed point on the slope, from a fixed point on the slope, right? And then measure the distance traveled, measure the distance traveled and the time taken. Then calculate the speed, calculate the speed using the equation, okay, using the equation speed equals distance over time. One possible source of inaccuracy would be that the time taken would be quite difficult to measure, okay? Source of inaccuracy, time taken would be difficult, okay? Okay, time taken would be difficult to measure. Okay, what about the table? Can I draw a table? Yes, table. What do I need in the table? I need the angle, the speed, and the angle, the distance, the time, and the speed, right? The angle in degrees. I know that the distance is constant, but it won't be wrong to write it down. in centimeters, the time taken in seconds, and the speed would be in centimeters per second. It's okay to write down the speed in centimeters per second. It doesn't have to be in meters per second, right? Centimeters per second. What about the conclusion? For each angle. For each angle. Repeat the experiment. Repeat the experiment and take average. Take average. And then record the readings. Record the readings in the table. In the table. And then compare the results. Okay. Compare the results by drawing a graph. Okay, by drawing a graph of the angle versus the speed. You need to plot a graph of the angle versus the speed. Okay.